pretty much call it a day, I think, and obviously the lab, and then we'll call it a day. But okay, so we've been talking here in this last chapter about equilibrium. Again, remember that basically equilibrium involves, as we've been talking about, a certain type of reaction, which are our reversible reactions. And those are the reactions that head in both directions. So they have a forward direction and a reverse direction. You could recognize them by the reversible arrows that you see written in the equation. And there's a certain relationship that happens, as we talked about, when something does reach equilibrium. So when something reaches chemical equilibrium, what that means is, again, the rate of the forward reaction will equal the rate of the reverse reaction. And at that point, there's a relationship that is basically constant that occurs. And that is basically the relationship of the products over the reactants. So, and that is basically what is known as the equilibrium constant, or capital K, which is basically the concentration of the products divided by concentration of the reactants. Now, the value of K does give us some information. So, as we talked about, it is really just a number. But if it's a large number, what that means is once we reach equilibrium, we would really mainly expect to see products there. When we have a small value of K and we reach equilibrium, we would mainly expect to see reactants present. And remember that basically one is sort of considered a large number. So anything above one is considered on the large side for K. Anything on less than one is sort of considered on the small side. We also talked about that if you do know the equilibrium concentrations, you basically can just plug it into the equilibrium expression and solve for the value of K. The other important thing is we do use the coefficients in the balanced equation as the exponents. So again, if there was like, you know, 2A goes to B, K would be the concentration of B over A, and we would square it because of the coefficient in the balanced equation. Lastly, there's really two things that do get included in the equilibrium expression, and that is things that are gases and things that are aqueous. So the G or AQ symbol next to something in an equation are the guys that end up in the expression. If you have something that is a solid or a liquid, so an S or an L, that's next to it in the equation, those guys do not get included. They really have no effect on the equilibrium, so we don't include them at all. Any questions on any of that stuff we talked about previously? So, sort of one of the last main topics here is what's known as Le Chatelier's principle, and I think this is where we left off. So, basically, the idea of Le Chatelier's principle is very simple. You sort of have a reaction that is at equilibrium. So you have A plus B, for example, goes to C plus D. So you got this guy that is at equilibrium, and basically you do something to it that essentially screws up the equilibrium. So that is sometimes referred to as you add a stress to the system. So when you add the stress to the system, it no longer is going to be at equilibrium. It's really going to get messed up. So you have the stress messes up the equilibrium. But eventually, what wants to happen is the system will once again want to basically get back to equilibrium. What are some stresses? As we will see, some stresses are concentration. So you could either add more or remove something. Volume and pressure are another stresses that you could do. Temperature is another stress that you could add. A catalyst as well. So again, in a lot of cases, when you do one of these things, add a stress to the system, it will cause, like I said, the equilibrium to really not happen at that point. So you're at a point where you're not having the same rate of forward and reverse reaction. So to fix that, what it essentially wants to do is either make more products, which means it will shift to the right, make more reactants, which means it needs to shift to the left. Or there is actually some cases where we might see here that you could actually get no change will occur. So no change will basically occur at all. And that's also another possible option. Yeah, so adding concentration, adding more reactants, adding more products, adding anything to this reaction is considered changing the concentration, which is a stress. So the question was, if we add more reactants, will that cause a stress? And it will. That's basically what concentration means. So if we wanted to add more something in this reaction that we're looking at, the A plus B, it'd be like if you went to the shelf and picked up some A and dumped it into the beaker, or B and dumped it in the beaker, or even C or D, just kind of grabbed it off the shelf and basically just kind of jumped it in there. That would be like adding more. And usually what that will do is sort of increase the concentration of those guys. So that's sort of what we mean by adding the concentration, or increasing or decreasing the concentration. Um, so what we're going to talk about is sort of each of these sort of effects on the equilibrium that will occur. So let's take a look at probably the first one here, which is concentration. So when we add concentration, there's basically two things that you could do. Um, you could either, with concentration, add more or remove. So adding more is pretty simple. Like I just mentioned, you pretty much could go to the shelf, grab the whatever you have in there, and dump it into the beaker, the flask, whatever you may be using. Removing, you usually don't want to reach into like a beaker, right, and grab out anything that's obviously a solution. You can't really grab things out. So a lot of times the way we could remove something in sort of Le Chatelier's principle is to cause a precipitate to form. So maybe you add something that's not there and it actually causes a solid to form. And if you remember, as we talked about, solid is not part of the equilibrium. So that's a very common way that we can sort of remove something, is to cause a precipitate to form. Another way we can remove something is actually to form water. Water is a pure liquid. That is obviously something that you can't necessarily see occur, but the formation of water can occur, especially with acids and bases. Especially if you have something with H plus and OH minus in there, you will make water. Again, visually, you probably won't see much going on, but that is a way to remove something like H plus or OH minus from a reaction that happens. So, basically, if you just kind of do it in terms of adding, if we just have a basic sort of, you know, seesaw type of thing here. And if we're at equilibrium here and we decided, hey, the guy on the left here is our reactant, the guy on the right is our products, let's add more guys to the right hand side. And if you do that and more people kind of hop on the right hand side here, what we're going to get is this sort of situation. Is award-winning stick figures here. There we go. So basically what just happened is, right, we put more people on the product side. So that messed up the equilibrium. So here we were at equilibrium. We added a stress. It messed up the equilibrium. So to fix that, we really need to put more people on the left-hand side here, right? More people need to hop on the left-hand side. So this equilibrium would shift to the left, and we would put more people on the left-hand side to fix that equilibrium. And once again, we would come back to that equilibrium state. So once we do adding, if we add more concentration, it is always going to shift away from the side you added. So what are we talking about in terms of side? Really in a beaker or something, there is no left side or right side. We're talking about the actual equation. So if you add more reactants, it will shift away and go towards the product side. If you add more products, it would shift away from the product side and go to the reactant side. So that's what we mean in terms of side. Obviously, again, if you're looking at a beaker, there's no left or right hand side. Everybody's floating around in there. But that's sort of what we're talking about here. So if you add, it shifts away. So AA is a good way to remember that, add away. And whichever side, again, in terms of the equation you added it to, it will shift away. What happens is after it sort of shifts away to fix that mess up of the equilibrium, it will once again come back to an equilibrium state. You may not have the same numbers of guys you started with on each side, but again, if you calculated K again, it would still be the same number as you started with. Again, remember that nothing changes the actual value of K except for temperature. So even though we added more one way or another, it will eventually come to that same ratio of products over reactants. Any questions on that there? So let's take a look at the example that we have here. So we have this reversible reaction. If we added more H2, so again, H2 is over here. And since we're adding, it goes away from the side we added it to. So we would expect it to jump to the right, basically, and basically make more products to once again reach equilibrium. If we added F2, that also is on the left-hand side here. So we're adding more reactants, again, shifting away from the side we added it to. We would also expect it to go to the product side. And lastly, if we added some more products in this case, if we added more products, that would be like adding stuff to the right. It shifts away from the right. We would expect it to go to the left. So when you add, it goes away. And again, whichever side in terms of the balance equation or the equation you're looking at that you added that to, it will go away from it. Now, as I mentioned, removing sort of the opposite, removing actually goes towards the side that you removed it from. So if we take my really bad stick figure example like we had previously, and again, the guy on the right, our left is the reactants, guy on the right is the products. Let's say the guy on the right-hand side hopped off in this case. If he hopped off in this case, we're going to get this situation here. In order to fix that, we need to go towards the right-hand side or the products where we removed it and put somebody else back on there. And now we would be back to equilibrium at this particular point. So when we remove, it goes towards, again, whichever side you removed it from. And again, you're going to be looking at the balance equation to figure that out. So here, if we removed H2, H2 is on the left-hand side, so it would go towards the side that we removed it from. F2, same deal. It is also on the left-hand side, so we would expect it to shift to the left-hand side or make more reactants to once again reach equilibrium. And lastly, if we sort of were able to remove HF from the system here, HF is on the right-hand side, which would cause it to shift towards the side we removed it from. And basically, in that case, we would need to make more products. Any questions on concentration? And as I mentioned before, that is sort of two very common ways that you can remove something from a equilibrium, make it precipitate, or make water. So how do you know maybe you did that? Well, sometimes in these type of problems, they say, hey, we added, something like, say, silver nitrate. Silver nitrate is nowhere in here at all. So whenever you sort of have a problem like this and they give you something that you're adding that is not seen in the equation, what you want to look at is basically these two things. You want to look at, will that thing react with something there and make a solid? So like solubility rules and stuff that we talked about. Or will whatever we're adding perhaps form water? In that case, probably something like H plus and OH minus are involved. But those are two things that sometimes occur and throws people sometimes for a loop. Is like they're told you added this thing, and when you look at the equation, you're like, I don't see any of it in the equation. So usually what that means is perhaps it's going to react with something in the equation. Any questions on that there? So that is one major stress that you could cause to a situation or an equilibrium condition. Another one is pressure, and really pressure and volume are really kind of tied together. So a lot of times pressure and volume sort of work together. If you remember pressure and volume, a lot of times pressure obviously involves gases. And if you remember our Boyle's law relationship, as the pressure goes up, the volume goes down, and vice versa. As the pressure goes down, the volume goes up. And that's sort of an important relationship here when we're dealing with the Chaitliers Principle and sort of pressure or volume changes that occur, especially when we have gases that are involved. And when we have gases that are involved, I personally think it's easier just to think about it in terms of volume. So in terms of volume, if the pressure goes up, the volume will go down, which means we have a very small sort of area for gas molecules to fly around in. What happens is as the volume goes down, pressure goes up. So we kind of want to bring the pressure back down. So in that very small area, we need less gas molecules. So this situation would shift to the side with the less gas molecules. Vice versa, if we increase the volume, everybody has more room to fly around with. Pressure starts to come down. We want to kind of bring the pressure back up. In order to do that, you pretty much need more gas molecules in this situation. So more gas molecules. Now, which side is that? It really does depend on the reaction you're looking at, you know, left-hand side or right-hand side. How do you figure out which side has more gas molecules? Well, you pretty much just look at the equation and the symbols and the coefficients. So if we looked at this particular reaction, on the left-hand side, there's a grand total of 2 gas molecules. On the right-hand side, there's actually a total of 2 gas molecules as well. So in this particular case, we do have sort of a tie on both sides here in terms of gas molecules. So if we increase the pressure of H2, it would not really shift to the right in this case because it's really a tie. So this is not necessarily correct per se, these answers. Because we actually do have the same relationships here. We have 2 gas molecules on both sides. So in this particular case, you actually get no change that would occur in each of these. So let's take a look at one that's maybe a little bit better here. Bad textbook example, apparently. We'll just do it like this. And we'll end up with, we'll just say 3C here. So if we look at this, on the left-hand side, we have 5 gas molecules. On the right-hand side, we have 3 gas molecules. So in this particular case, if we increase the pressure, that means that the volume would go down. Again, really pressure, and we'll just pick up from this slide here. If again, the pressure increases, volume will decrease. So again, in that situation, as we talked about, we want to go to the side with the least number of gas molecules. And again, if the pressure decreases, the volume most likely will increase in that case, and we'll go to the side with the most number of gas molecules. All right, so if we look at something like this here, we have this reaction here, and let's just say that we increase the pressure here. That means that the volume would decrease in this particular. Means that we would, in this case, look at this guy. We have 4 gas molecules on the left and 2 on the right. And in this particular case, we would want to shift to the side with the least number of gas molecules. So it would shift to the right in this particular case, as the right-hand side has the least number of gas molecules. If we did sort of the opposite here, we decrease the pressure and increase the volume. Opposite is going to happen here. Bigger, which is on the left-hand side, so it would shift to the left-hand side in this particular case. Any questions on that there? I'm assuming you can still hear me, even though I think I might have been frozen again. So we'll take a look at this one. So why don't you take a second and see what happens in this case. So for each of these here, try to determine, will it shift to the left? Will it shift to the right? And you know, or will there be no change on this particular? Let's say we did each of these, we added that, we decreased the volume, and we removed that. Is on the product side, which means it should shift away from that. So it should cause it to shift to the left in this particular case. So if we added more PCl3, which is a product, it should shift away from it. And again, we should end up getting more reactants in that particular case. Now, if we decrease the volume, so if the volume goes down, that means we would expect the pressure to go up. But again, here looking at really the volume, that is a smaller volume, which means we really want the side with less gas molecules. So in this particular case, there is one gas molecule over here. There is a gas molecule here and here. So that is two gas molecules. So in that case, if we did decrease the volume, we would actually shift to the left as well. Again, that is the side with the least number of gas molecules that are basically there. Lastly, if we remove PCl5, that is a reactant. So when we remove that, it's going to shift towards the side that we removed it from. So we should expect it to shift to the left. Any questions on any of those guys there? All right, so that is pressure and volume. They're basically kind of tied together usually. And again, volume is usually a pretty good one to look at in terms of what is happening. Another stress that you could do is temperature. Temperature works the same as concentration, which means if you increase the temperature, it will shift away. If you decrease the temperature, it will shift towards. And what basically determines sort of which way that is what type of reaction it is, whether it's endothermic or exothermic. So if you remember, endothermic means heat and energy is given off. Another way that we display an endothermic reaction is with the delta H value that is positive. So again, doesn't matter really what the number is, but if you see a positive value for delta H, that means that it is going to be an endothermic reaction. And basically, what that means is heat and energy is being absorbed. And what we think about in terms of energy, heat, and temperature is in an endothermic reaction, it's thought of as being a reactant. So that's what the E stands for here. It's thought of as being the energy in an endothermic reaction, which means if we increase the temperature, that would be like adding more energy here. It should shift away and go to the right. If we decrease the temperature, that's like removing energy, which would be like removing a reactant, which means it should go towards that side and go to the left. So adding or removing temperature, increasing or decreasing temperature is basically what you're doing there. Works the same way as concentration. You just need to determine is it endothermic or exothermic. And again, very commonly sort of given to you is this number here at the end of the reaction. And that sort of tells you, sort of what it is. Um, if we had an exothermic reaction, works kind of the same way, except that if it's exothermic, heat and energy is being given off. So energy, heat, temperature is thought of as a product in this case, which means if the reaction is exothermic, you will also see the delta H value being negative in this case. And that means if we increase the temperature, it's like adding more energy to the product side, and that should shift away, which means it would go to the left. If we cooled it down, put everything on ice, that would be like removing energy, and that would then shift it towards the side we removed it to, which would go to our right hand side in this particular case. So it definitely is based on whether it's exothermic or endothermic as to sort of what is happening. Question on temperature. So let's take a look at one here. Let's just take a look at this one and we'll just kind of do some different questions here. So take a second to decide what would happen if we added more SO3. We removed O2. We let's go with increased the volume. Let's go with let's go with increasing the temperature, and let's say adding SO2, and we increase the pressure. All right, take a minute and. Okay, so let's take a look at this. So first one is we're going to add more SO3. So adding SO3 is on our product side. When we add it, it shifts away. So since it's a product, it would shift away from the product side, and we would expect it to shift to equilibrium basically to the left-hand side. Now, if we remove O2, so O2 is over here. When we remove something, again, it goes towards the side we removed it from. So since the O2 is on the left-hand side, it would cause the equilibrium to also shift to the left-hand side in this particular case. Any questions on those two? Now we're going to increase the volume. So remember that if we sort of increase the volume, that means really the pressure is going to go down. But the volume part is kind of the important part here. In a bigger volume, we would need the pressure to come back up. In order to do that, we need whichever side has the most gas molecules. So over here, there are 3 gas molecules. Over here, there are 2 gas molecules. That means in this case, it would also shift to the left here in this example. We need to increase the temperature. What's going to help us is here, this is a delta H value, which is the enthalpy for this reaction. Number really is not important. What's important is right there. That is a negative number, which tells us that this is exothermic. And that means if we added heat or energy, we would add it to the product side as it's exothermic. And we're going to increase the temperature, which means it's like adding more products, which means it's going to shift away from it. I picked all left so far, huh? So it's going to go to the left-hand side here. Any questions on that? So again, this is very commonly how it's sort of given to you in these type of problems. You're just given the delta H value, and really you just need to look, is it negative or positive as to whether it's endothermic or exothermic to determine that. Here we have SO2 being added. SO2 is over here on our reactant side. So we're adding it. It goes away. We finally got one to go the other way. There it is to the right-hand side. And lastly, here we're going to increase the pressure. So again, if we really increase the pressure, volume should go down. Again, looking at that volume going down, that is a smaller volume, which means we want less gas molecules. So we would expect it to shift to the right. Question on any of those there? One last thing that you can sort of add to an equilibrium that you sometimes see is to add a catalyst. And I think we talked about catalysts a little bit earlier, but catalysts basically speed up a chemical reaction. They do that by lowering the activation energy, so it has a smaller hill to climb to get to the other side. But if you add a catalyst to a system at equilibrium, it will actually have no change. So that's one very popular way or common way you could get no change to occur. Also, something like if you added, say, a noble gas, that also would cause a no change situation. And also, what would cause a no change is sort of what we had in that earlier example. Perhaps you had the same number of gas molecules on both sides, and you increase the pressure, decrease the pressure, did something like that. In this case, because it's a tie, it would cause a no change situation as well. So those are sort of 3 common ways you could get kind of a no change, no shift to occur. Adding a catalyst, adding something like a noble gas. And again, noble gases are chemically inert, so they don't really participate. And lastly, sort of an equal number of gas molecules on both sides. Since there is no side that's more gas molecules or less, it basically will cause no change to occur. Any questions on Le Chatelier's principle? So ultimately here, we're looking at concentration. If you add, it goes away, whichever side. If you remove concentration, it goes towards it. Pressure and volume, again, thinking about it in terms of volume, increasing the volume, more gas molecules, decreasing the volume, less gas molecules. And temperature works the same way, again, as concentration. You need to determine, is it endothermic or exothermic, and then decide increasing will shift away and decreasing would shift towards. Any questions on any of that there? Okay. So obviously in an exothermic reaction like this one, if we increase the temperature, it goes to the left. If we decrease the temperature, it goes to the right. Endothermic would be opposite as well. If you increase the temperature, it goes to the right. Decrease it, goes to the left. All right, we'll skip that one. Why don't you take a second and think about this one? For this reaction, a reaction at 25 degrees Celsius, the value of K is 1.2 times 10 to the minus 3. If the temperature gets raised to 50 degrees, the K value goes to 3.4 times 10 to the minus 1. Is this reaction endothermic, exothermic, or do you need more information? So take a second or so. To a temperature of 50 degrees Celsius, our K value becomes 1.2 times 10 to the minus 3. Remember that when we calculate K values, it essentially is products divided by reactants. So what we see is as we increase the temperature, the K value also increases. So we increase the temperature, K value gets larger. Only way to get a K value larger is you need more products, right, to do that. So basically, you want to figure out, you know, which way will allow us to make more products. So since we're increasing the temperature, it needs to go away from the side that it's on, which means that in this particular case, heat or temperature would have to be on the reactant side. So when that we increase the temperature, it shifts away. When it shifts away, makes more products. Making more products gives us a larger K value in that particular case. That means that since the heat has to be on the reactant side, this would be an endothermic reaction in this particular case. Again, if the opposite was true and it was exothermic, we would actually see the K value go down in this particular case because it would be over here. It would shift it that way. We would make more reactants. Any questions on sort of the reasoning behind that there? We also see what we talked about. Again, as we increase the temperature from 25 to 50, we do see an increase in the K value. And again, we actually see a different K value. So as we talked about, temperature again is the one and only thing that will actually change the value of K. But as we would be in this situation here, if we kept it at 50 degrees Celsius, the K value should maintain at 3.4 times 10 to the minus 1. If we dropped it back down to 25, it should drop back down to 1.2 times 10 to the minus 3 and be able to maintain that. Any questions on that there? All right, so we're going to talk a little bit about specific solubility equilibrium. I'm not sure why we are, but we'll talk about it here, I guess, in this class. This is really something that you'll see in Chem 1B. And it's in the hardest chapter that you'll take in Chem 1B is this stuff, but this particular topic here. But this solubility equilibrium is a type of equilibrium. It really is just an equilibrium constant. As I mentioned earlier in this chapter, there's all kinds of Ks like Kc, Kp, we've seen Kw, there's Ka, Kb, KSP, KF, and so forth and so forth, also known as Chem 1B when you get there. That's pretty much, again, all you talk about is every single K value you could ever imagine in that particular sort of class. But all these guys really are just really basically the same thing we've been talking about is products over reactants, basically. And one specific one is known as KSP. SP stands for solubility product. So that's what the SP stands for. So solubility product. And as you could probably imagine from the name, it involves sort of solubility rules. It is really an equilibrium, which is kind of an odd equilibrium. It's an equilibrium for things that are typically insoluble. So typically, if you look at, like, say, those solubility rules, anything that's sort of insoluble based on that will set up an equilibrium. So for example, if we had something like silver chloride, when we think about silver chloride, it is a solid. So we think about it as a solid, but even though it is a solid, it actually will set up an equilibrium where it would break apart into its ions, something like this, silver ions and chloride ions. And we can write an equilibrium expression for this, which would be the KSP is the silver ion times the chloride ion in this case. We would not include our reactant because, again, it is a solid. So, again, it's not included. So, specifically with KSP type problems, pretty much it's always going to be just the products because the reactants are always solid. As you can see here, sort of the general format to ions or aqueous. So, definitely specifically dealing with KSP type problems, you always have solids on this side. So, they never find themselves into the equilibrium expression in this particular case. Um, so here's another one. Again, we do it the exact same way. We have this bismuth here, which is a solid, again, breaking apart into its ions. And if we were to write our KSP, we would still take the coefficients as the exponents. So our 2 here becomes squared, our 3 here becomes cubed. And we get our KSP sort of expression for this. Again, we have no reactant involved in that particular case, again, because it is a solid. The KSP, like any other equilibrium expression, all those Ks that I listed earlier, they are all still going to be unitless. They're just numbers basically involved. Even though, let me see your question there. Not necessarily. It has to do with necessarily how much can be dissolved. So it is a kind of a special equilibrium KSP involving really things that, as I said, are insoluble. So sometimes we think about things like I said, the silver chloride or what we got on the bottom there as being a solid, which means it's like 100% going to be a solid no matter what the situation is. And it's really not true. That particular like hard cutoff is a solid. 100% of it's a solid, even though things are technically considered insoluble based on sort of solubility rules. Everything has some degree of solubility, which means even things like silver chloride, which are technically almost 100% insoluble, going to be a solid, there is still a super small amount of it that will break apart and basically make ions. Um, so that's why we do have these equilibriums that are set up. Even though if you had something with silver chloride, pretty much visually, you're going to see pretty much, you know, all of it over here. But there is a small, super small, like sometimes even to like times 10 to the minus 12 in terms of concentration, like almost is pretty much not there. But there's just a super small amount that will still remain basically ions in solution, even though 99.999% of it is a solid at that particular point. Um, and that goes with everything. Sometimes something else you also learn if you take Chem 1B is, again, we sometimes think about those solubility rules as being like 100% always going to happen no matter what the situation is. But there's actually a lot of things that affect solubility. Things like pH affect solubility, things like other ions that are present. So even though based on solubility rules, for example, you could have a situation where you have silver and chloride together, but based on something maybe like pH, based on concentration of the ions that are present, you may actually not see the solid form. So there's a lot of things that actually do affect solubility, even though sometimes from like this class, the next class, you get those solubility rules in your head and you think it's like 100% always going to be that no matter what the situation. But there's a lot of situations that can kind of affect the pH. I'm not sorry, the solubility of it. Um, that's why also if you ever see a table, which we don't have here, but if you ever see a table of KSP values, they are really super small values, very small. And what that means is basically what you would mainly have when you reach equilibrium are reactants. So you mainly have your reactants present at equilibrium because they're really small, which means almost 100% of it stays as a solid. But again, you do have a very small amount that will go the other way. So if we look at, say, a problem like this, we wanted to calculate, we have a lead to chloride this made by dissolving some salt in some distilled water. We get a concentration of lead that is 1.6 times 10 to the minus 2. What will be the value of KSP? One way that we typically do solve equilibrium problems when we are not given the equilibrium concentrations or anything like that per se, um, is we sometimes use an approach which are sometimes referred to as ice tables. And ice table stands for initial, change, and equilibrium. And basically, we use an ice table to figure out, what something will be at equilibrium if we're given sort of the initial concentrations of everybody. And I'll show you how to kind of do that with this problem, even though technically speaking, you don't really need to do an ice table, but I'll just kind of show you how it works. So the first thing you would do is take, say, your salt or something like this and your reaction, and you would break it apart and have the overall reaction, which in this particular case would look something like this. Again, this is basically just going to be a salt that's breaking apart into ions. We can write our KSP for this. Actually, I'm going to write it up here. Our KSP for this would be our products, which would be the lead 2 times our chloride, and we would want to square it because of the coefficient that's here as well. Now, if we were to do an ice table for this problem, which again, you don't actually necessarily need to, an ice table would look something like this. So because the solid really is not involved in equilibrium, we really don't do anything with it. We just kind of leave it alone. When we go to our product side, we could safely assume if we are not told anything that we're starting with 0 in terms of the amount of each of those guys. The change part is the part that basically takes care of the stoichiometry when you do these type of problems. And in this particular case, it's usually a pretty safe assumption that the reaction is heading towards the product side, which means if the reaction is heading towards the product side, all of our reactants should be decreasing with time, and we use a minus to represent that. Now, on the product side, we should be increasing the amount that we're making with time, and those guys are represented by pluses. So what we would have here is plus x. You could actually use s or any letter, but x is common, plus 2x here. The 2 is because of the coefficient, and the coefficient here is 1, which is why it's 1x. Again, we're not going to do anything here on the reactant side because it's a solid. That means when we get to equilibrium, we would have x and 2x at this point. Basically, we just bring it down to the end. First off, any questions on sort of what the ice table looks like here? Again, if we did have something on the left-hand side that wasn't a solid, we would probably have a number here. We would have a minus x or something like that. But again, in this case, since it's solid, we don't have to worry about anything at that particular point. The goal usually is, we want to kind of solve for what x is when we do know the k value. In this particular case, we don't know the k value. That's what we're trying to find. So we could still do the same thing. We could take our expression and basically put our values in there, which would give us x times 2x squared. Basically just taking these guys at the equilibrium and basically putting them into here. Now, the one thing that we do know is when we reach equilibrium, we do have a concentration of lead that is 1.6 times 10 to the minus 2, which if we look at our table, we could see that is what x equals in this particular case. So we actually do know from the problem that x is equal to 1.6 times 10 to the minus 2, and that is this x here and also this x here. So we actually have everything we need. We could go and go 1.6 times 10 to the minus 2 times 2 times 1.6 times 10 to the minus 2, and we do need to square it in that particular case. And if we do all that, we will end up with 2 times 1.6 to the minus 2 squared times 1.6 to the minus 2. And it looks like it is, I think, D looks like a winner here. Looks like 1.6 to the minus 5. It is still a K value, which means you do not have to put units or anything like that. Any questions on sort of that step there? Okay, so let's take a look at a different sort of ice table. And you roll through this, but I think they actually have the wrong answer here as well. Bad textbook examples today. So they had all that right, but that was right. That was good. All right. All right. So calculate the solubility of silver chloride with a KSP of 1.6 times 10 to the minus 10. So let me show you how we would do this problem. In this case, which is a little bit different than the one we just had, we're actually given the K value and that's it. We're not given any other information. So we would start with our silver chloride, which is this. It will again break apart into its ions. And we could write our KSP, which would be the concentration of silver times the concentration of chloride, and that equals 1.6 times 10 to the minus 10. So in a case where you're just given the K value and maybe initial concentrations or no concentrations, you usually do have to do an ice table. So we'll kind of show you again how that looks. So we're going to do our initial. Again, we're not going to deal with anything here because it's a solid. We're going to assume that we're starting with 0 of each of these guys. We're also going to probably safely assume that this reaction is going to head to the product side, which means my reactants will be minuses. My products would be pluses. So we'll do plus X and plus X. Again, the coefficient here is 1 for each of these, which is why we don't have anything like 2X or anything like that. So plus X on this side, which means when we get to equilibrium, we end up with X and X. Any questions on the ice table there? In this particular case, we want to figure out actually what the solubility of silver chloride is in water. So we're going to now take our KSP expression and put in our values that we got at equilibrium, which means that it would basically be X times X, and that's going to equal 1.6 times 10 to the minus 10. At this particular case, that means we have x squared is equal to 1.6 times 10 to the minus 10. We want to do a little square root of that probably there to figure it out. And if we take the square root of that, we will end up with we'll end up with x that is equal to 1 point, we'll call it 3 times 10 to the minus 5. Now, you may be wondering what these numbers really are. These numbers, typically in an ice table, when you are using them, they typically are molarity, which is moles per liter. So this is really the molarity of the silver ion would be 1.3 times 10 to the minus 5. It's also the molarity of the chloride ion, 1.3 times 10 to the minus 5. It is a 1-to-1 relationship going backwards, which means the solubility, and when we're talking about solubility here, that is the molar solubility is sometimes referred to. It is also sometimes referred to as S, the molar solubility. And that would be for silver chloride, 1.3 times 10 to the minus 5 molar. And just for a sort of a reference point, if we wanted to figure out what that means in, say, grams per liter, so this is moles per liter, we could take the molar mass of silver chloride, which was like 107.9 plus 35.45, and we could times that by 1.3 to the minus 5. That tells us that if we do that, there we go. We end up with something like, if we multiply it by 143.35 grams per mole, something like, what we got there, 0.00186 grams per liter. So what does that number represent? That number represents, that is how many grams of silver chloride you could get to dissolve in 1,000 milliliters of water. 0.001 grams, basically 0.002 grams. That is not a lot. Yeah. So and that's why when we think about something like silver chloride, we usually think about it as being a solid, as in normal conditions. You pretty much can get only about 0.002 grams to dissolve in like 1,000 milliliters of water. And that's why, again, we typically see it as a solid. Any questions on that? So when we talk about solubility, sometimes in relationship to KSP problems, and instead of X's here, sometimes also people will use S's in place of it. And the S stands for molar solubility, basically. Any questions on sort of that ice table type of problem there? All right. Just to go over a non-KSP type problem, just to show you how it sort of works as well. Hopefully they got the same number we got there. They did, so that's good. Let's take a look at just maybe one where it's not necessarily a KSP problem, but just a regular equilibrium type problem. So let's say we had we'll do H2 plus I2 makes 2HI. Just two gases on everybody here. It's good. And 222. We'll say the K is like 54 or something like that. And let's say we started with 0.5 molar H2 and 0.5 molar I2. We want to know what is everyone's equilibrium concentrations. So the numbers that we're given are not equilibrium concentrations, they're initial concentrations. And the goal here is we want to kind of figure out what is the equilibrium concentration of everybody. This is definitely a situation where you would want to use an ice table. And again, to show you how it works, we would take our initial, and in this case, we do have an initial concentration of H2 as 0.5 molar. We have this guy, which is 0.5 molar. And if you're not given anything on the product side, again, it's safe to assume that you're starting with 0 in this case. So that's typically the way we would set a nice table up for a problem like this. We also can safely assume that this reaction is heading towards products because we're not starting with any products. So that's a pretty safe assumption. That means that our reactants should be decreasing. So those should be minuses. Our products should be increasing. Those should be positives or pluses. So the change part here would be minus X, minus X. Again, the coefficient here is 1 in each of these, which is why it's just X. On our product side, it should be increasing, and that would give you plus 2X. The 2 here is really important because that takes care of the stoichiometry part, the mole to mole relationship that keeps everything correct in terms of that. So very common people kind of screw up the change part by not taking into account those coefficients. And when you do so, you're going to basically be messing up that mole to mole stoichiometry relationship, and you will get the wrong answer. At this point, we essentially just going to carry down everything to the equilibrium line. So we would have 0.5 minus X, 0.5 minus X, and 2X. Any questions on the table there? Okay. What we would want to do now is write our equilibrium expression, which would be our products, which would be HI, and we would want to square it because of the coefficient, divided by our reactant, which is H2 and I2. And in this case, that does equal 54, which was given to us here in the problem. At this point, we're going to do... Yeah, so the minus here is the minus is on the reactant side because in this particular reaction, we just put it this way, right? So in this particular reaction, or in a majority of these ones that you do, when we start this reaction, if we initially only have reactants and no products, pretty much your only option for this reaction to happen is this reaction pretty much needs to start in the forward direction. because it can't go in the reverse direction at this point because you have no products, right? In order for the reaction to kind of go the other way, you need some products to do that, right? They need to break back apart to go to the reactants. So since we're starting here with no products, it is safe to assume that the reaction will pretty much start exclusively going in the forward direction. And what that means is in order to make products, we actually have to lose, right? Some of our reactants, they have to basically be used. And that's why they become negative on this side. While we're doing that, as we're using up some of our reactants, we're going to basically start making some products at that point, right? And when we make products, they're represented by sort of a positive, like we're increasing the amount of it. Any questions on that? So I won't say 100% of the time you ever do an ice table in your life, if you plan on doing a lot of ice tables, that uh, it's minuses on the left-hand side, pluses on the right-hand side. But, you know, probably in most cases, 99% of the time, it's going to be minuses or x's because that represents the change part. So what we're assuming is the reactants are decreasing with time. So that's why it's minus x's, while the products are increasing with time. So that's why it's plus x on that side. But probably 99.9% of the time, that is sort of the setup that you would have. Minuses on the left, positives on the right. Other questions on that? Okay. So again, that's basically what the X represents is the change. It's basically how much H2 is being used up. Minus X here is how much I2 is being used up. 2X is stoichiometry compared how much HI we're making at that particular point in that particular case. So once we have this ice table here, we then want to put all those values into our expression. So basically what that means is we would have 2x. We still need to square it because of this. We would then put in 0.5 minus x, which is this guy, times 0.5 minus x, which is this guy as well. And that's going to equal 54 in this particular case. Now, there's multiple ways you could solve these type of problems. Some involve quadratic, which again, formula. If you get into 1B, you'll do a lot of that, assumptions and all that good stuff. But for us, I'm not sure we're seeing many of these, but in this particular case, if you look at it, it actually is a perfect square on both sides. You just put a big giant square root over both sides there. And if we square root the guy on the left, we end up with 2x on top. We end up with 0.5 minus x on the bottom. And the thing I always forget to do is actually take the square root of the right-hand side there. So square root of 54 going to get us something like 7.35, we'll call it. At this point, it's just a math problem we could solve for x. We're going to multiply the bottom to the other side. So we're basically going to multiply 0.5 minus x to that side. When we do it on this side, it's going to cancel. That's going to give us 2x is equal to 3.67 minus 7.35x. We're going to bring all of our x's to the same side. So we're going to bring this guy back to the other side. And if you do that, you will end up with 9.35x is equal to 3.67. Going to divide that to the other side. Going to get us 0.393 as our x value. Any questions on that so far there? So what is that x value? That x value is every single x here. So we would then take our x value and basically put it into there. So I'm just going to flop the page here for a second. So for our H2 at equilibrium, we had 0.5 minus x. For our I2, we had 0.5 minus x. And for our 2HI, we had 2x. So putting in our number, we get 0.5 minus 0.393. That gets us 0.5 minus 0.393. 0.107, and it would be molar. We would do the same thing here. We would get the same answer since it's the same number. And here we would take 2 times 0.393, and that would get us 0.786. And these three numbers would represent the equilibrium concentrations of everybody once this thing reaches equilibrium. And we do see what we would expect. We started with 0.5 of H2, ended with zero point 0.1. So the amount of it decreased as this reaction reached equilibrium. Same thing with our I2. We started with 0.5, ended with zero point 0.1, also decreased. And we started with 0. If you remember, this guy ended with 0.786, increase with time, which is what we would expect to have more products. First off, any questions on any of those numbers, where any of them came from, why we did any of those there? The nice thing about this, and 1B, if you take 1B, is it's math, so you can actually check yourself to make sure you didn't screw up somewhere. And we could do that by just simply putting these equilibrium values back into K. And if we did that, 0.786 squared divided by 0.107, 0.107, and you roughly get something like 53.96, which is 54 for our equilibrium constant, which again is the same number we got here, we started with. So the nice thing about some of these equilibrium problems is it really is math, so you can kind of do a good amount of math and you can check yourself at the end. Any questions on that there? All right. That's it. Yeah, that's all she wrote, I think. That's it for the semester. Congratulations. We have now finished Chem 3 in terms of lecture. And we're kind of out of here on lecture. So we will have one lab, which is Le Chatelier's principle. We're going to do that so you at least can see the Le Chatelier's principle and all that good stuff. The reason I kind of showed you the ice table is I think there's a couple of post-lab questions that involve ice tables, so at least you could kind of do those as well. I think the last one's similar to what we just did here on this particular example, so you'll be able to finish those as well. In terms of the final for this stuff, you need to know the equilibrium stuff in terms of basically calculating the equilibrium constant, what it is, if you have some equilibrium concentrations, and be able to put them into obviously the expression like we did previously before today. You do need to know the Le Chatelier's principle stuff. I don't think you have to worry too much about ice tables for the final and stuff like that. But you do need to know kind of, I would say, from Le Chatelier's principle back to the start of this chapter, if that sort of helps. I really don't understand why they put it in this class, these things at the very end here, but because you'll never see it again until 1B. But we'll go with Le Chatelier's principle, and before, in terms of stuff we talked about here in this chapter, is what you need to know about. Any questions on any of that stuff there? So again, we'll do the final experiment here, which is the Le Chatelier's principle one, and then we'll wrap it up for this semester, I guess, and we'll talk about finals and all that good stuff in lab after we're done with that. All right, make sure